Slide 1. Deep Sea Sediments, Topic 11b. Slide 2. Kinds of sediments. Sediments are particles, broken pieces, bits of stuff, that cover the ocean floor. Ocean sediments are typically divided into 4 categories: rocks carried off the land, lithogenous sediments, shells and other remains of dead organisms, biogenous sediments, chemicals that solidify out of ocean water, hydrogenous sediments and dust and other particles that fall from outer space, cosmogenous sediments. By far the 2 most common kinds of sediments are lithogenous sediments, bits of rock, and biogenous sediments, typically shells, mucus, and fecal matter. In special places, hydrogenous sediments are common on the ocean floor, like the sulfides that solidify out of ocean water at hydrothermal vents or salts that solidify and coat the bottom of warm water lagoons as water evaporates away. When chemicals join together to form solids in a liquid, we say that they precipitate, similar to how water molecules join together in air to produce liquid rainwater or solid snow, what we call precipitation. These categories are somewhat arbitrary, because all sediments are really a mixture of all 4 kinds of sediments. We typically classify a sediment sample according to whichever kind of sediment is dominant, whichever kind of sediment is the most abundant. In fact, we call a sediment biogenous if at least 30% of it is composed of the remains of ocean life. Thus, a sediment could contain nearly 70% rocks, and still be called biological. The reason for this is that rocks are the most common kind of seafloor sediment, and if we did not lower the standard for biogenous sediments, then almost all ocean sediments would be classified as lithogenous, even when they contain unusually substantial amounts of biological material. Slide 3. Key things to know about lithogenous sediments. Lithogenous sediments are carried to the coast by rainwater runoff, rivers, and winds, then currents and winds carry them from the coast out into the ocean. Larger sediments are left up in the mountains or along beaches, because they are heavier and sink quickly to the bottom, so after they have reached the shoreline, winds and currents cannot carry them far into the ocean before they settle to the bottom. This includes sand. Sand cannot get very far from land. Sand does not move very far out into the ocean, because it sinks quickly in water. Sand only moves down rivers and beaches, because rivers and beaches are shallow enough that waves and currents can pick sand grains up again and again each time they fall to the bottom. Only the smallest sediments, like mud, silt, and clay, can get carried far out into the ocean, because they are very small and light, and thus sink very slowly. Even so, at some point in their journey, most small sediments sink below where waves and surface currents can lift them up. Once sediments sink beneath the reach of waves and surface currents, they continue sinking and eventually reach the ocean floor. A few lucky sediments, though, get lifted up by wave orbitals again and again and travel hundreds or even thousands of miles before finally sinking below the reach of the waves. The tiniest can be kept aloft by strong, fast winds in a similar way. Thus, the important rules to remember for lithogenous sediments are: larger, heavier lithogenous sediments like sand sink faster, so they settle on land or next to the land. Most small, light lithogenous sediments like mud settle close to the land, because they come from the land and sink. However, since they sink very slowly, a few of them occasionally get carried out into the middle of the ocean by currents and winds. The small lithogenous sediments that travel far from land and reach the deep ocean floor are called red clay or abyssal clay. Abyss means bottomless or deep. Most sediments are transported long distances by ocean currents, rivers, waves, and the wind, but there are other things that can move sediments significant distances. For example, glaciers push sediments from the land into nearby coastal waters. Some sediments get stuck in glaciers that flow into the ocean and break off as icebergs. When the icebergs melt, the sediments fall to the ocean floor. This is a way in which large sediments can be carried to the middle of the ocean and reach the deep ocean floor. Slide 4. Key things to know about biogenous sediments. Biological sediments are referred to as oozes. There are 2 kinds of ooze, calcareous ooze and siliceous ooze. Calcareous ooze consists primarily of calcium carbonate shells, and siliceous ooze consists primarily of silica shells. Most dead, decaying bodies and fecal matter are dissolved by ocean water, decomposed by bacteria, or consumed by animals as they slowly sink towards the bottom of the ocean. Only a small amount reaches the deep ocean floor, often no more than 1%. Thus, the important rule to remember for biogenous sediments is: most biogenous sediments dissolve before reaching the bottom. The longer it takes biogenous sediments to fall, the more they will dissolve before reaching the bottom. If the ocean is too deep, biogenous sediments will dissolve away completely before reaching the bottom. No biogenous sediment will be left to pile up on the ocean. Most biological sediments consist primarily of calcium carbonate or silica, substances that some phytoplankton and zooplankton make their shells out of. The other parts of the organisms tend to get decomposed by bacteria. Only the shells remain. Slide 5. Silica is most common on the ocean floor beneath cold surface water, because silica dissolves rapidly in warm water. It dissolves in cold water too, just more slowly. Calcium carbonate is most common on the ocean floor beneath warm surface water in places that are not too deep. Calcium carbonate dissolves rapidly in cold, carbon dioxide-rich ocean water under high pressure, precisely the conditions that are common in the deep ocean. Thus, it does not sink too deeply before it dissolves into the ocean water. Cold water can hold more carbon dioxide than warm water, so it is more acidic, and therefore dissolves the calcium carbonate faster. Calcium carbonate does not dissolve at all in warm water. In fact, calcium carbonate dissolved in ocean water will solidify, precipitate, in very warm ocean water. It forms small chunks on the ocean floor called hoolites which roll around in the waves, smoothing them. Some corals make little homes for themselves, shells or exoskeletons, out of calcium carbonate. It is easier for them to solidify calcium carbonate in warm water. This is one reason that coral reefs grow in warm, tropical places. The falling material often ends up clumping together, so you can actually see it with your own eyes. It glistens when deep-sea explorers shine their lights on it, so it goes by the nickname marine snow. Calcium carbonate sediments often end up coating the top of underwater mountains like the mid-ocean ridge, but not their sides, because the sides are too deep. The calcium carbonate sediments completely dissolve away before reaching the bottom. We call the depth at which the shells have completely dissolved the carbonate compensation depth or CCD. Once the shells reach the top of the underwater mountain, they get buried by other sediments and will not dissolve anymore, because they are no longer surrounded by the ocean water. Something similar can happen to silica shells, though they are often found deeper than calcium carbonate shells. Since silica dissolves slowly in cold water, it can travel farther down before completely dissolving away. Oozes, biological sediments, on the ocean floor are decomposed by bacteria and dissolved by ocean water. This means that if there is less water around them, they dissolve slower, because there are fewer unbonded water molecules available to bond with the molecules of the oozes. In fact, the water closer to the bottom can become supersaturated with dissolved chemicals if lots of ooze is sinking down. In other words, nearly all the water molecules are bonded to and grouped around other molecules, so the water molecules cannot bond with the molecules of the ooze and pull the ooze molecules away from one another. In other words, biological sediments remain solid, do not dissolve anymore in supersaturated water. Slide 6. Coastal ocean sediments. The continental shelves, shallow, flat areas close to the coast, are really part of the continents. When sea level is lower, like during an ice age, they are weathered and eroded like any other place on land, so the sediments on the continental shelves can resemble sediments from the land. In other words, continental shelves tend to have lots of larger sediments on them like sand and gravel, not just mud like the deep ocean floor. These sediments are often called relic sediments because they are left over from when sea level was lower. Once sea level rises again, other sediments like mud and plankton shells pile up as well and mix with them over time. We will call this mixture of sediments continental material. Sometimes some of the gravel, sand, mud, and plankton shells on the continental shelf can spill over the edge of the shelf, slide down the continental slope, and end up on the deep ocean floor near the bottom of the slope. Huge, underwater avalanches, called turbidity currents, can carve out canyons along the edge of continental shelves. Slide 7. Distribution of deep ocean sediments. To understand where each kind of sediment is the most abundant kind of sediment on the deep ocean floor, we need to apply the following information. Calcareous ooze does not dissolve in warm water, but dissolves rapidly in cold water. Siliceous ooze dissolves slowly in cold water and rapidly in warm water. The deeper the ocean is, the more time oozes spend in contact with ocean water, which can dissolve them and thus prevent them from reaching and building up on the ocean floor. Red clay does not dissolve, so it always reaches the ocean floor. There is a lot more calcareous ooze or siliceous ooze in surface water than red clay out in the middle of the ocean, far from land, because oozes are primarily made of the shells of the animals and algae that live out in the ocean, far from land. On the other hand, red clay has to travel hundreds or thousands of miles from land to reach the middle of the ocean. Very little red clay gets this far out into the ocean. Most red clay ends up sinking closer to land. Calcareous ooze, calcium carbonate shells, is the dominant sediment beneath the warm surface water of the mid and low latitudes where the ocean floor is not too deep, like on top of the mid-ocean ridge, sea mounts, underwater mountains, and the outer edges and slopes of wide continental shelves. Recall that calcium carbonate dissolves rapidly in cold water, it is more acidic from excess carbon dioxide, while silica dissolves rapidly in warm water. Thus, calcareous ooze is more abundant than siliceous ooze in places where the surface water is warm at the surface and not too deep, because most of the silica shells dissolve at the surface. The calcium carbonate shells do not begin dissolving until they reach the colder water beneath the surface, and the shells do not dissolve much on the way down, because the ocean floor is not too deep, so they do not have much time to dissolve before reaching the bottom. Once buried, the calcium carbonate shells are no longer in contact with the ocean water that dissolves them and thus no longer dissolve. Calcareous ooze is more abundant than red clay not too deep water far from land, because calcareous ooze is the remains of plankton who grow in the middle of the ocean, far from land, whereas red clay has to travel out from the land. Most of the red clay coming from the land does not reach the middle of the ocean. Like all sediments, red clay sinks in water, and red clay sinks as it travels from the land far out into the ocean. Most red clay ends up sinking closer to the land. A few lucky pieces keep getting lifted up by waves again and again while being pushed outwards by currents, or kept aloft by strong winds. Very little red clay reaches the middle of the ocean, so there is much more calcareous ooze than red clay sinking towards the bottom far from land. Siliceous ooze, silica shells, is the dominant sediment beneath cold surface water and where the ocean floor is not too deep, like on top of the mid-ocean ridge and sea mounts, underwater mountains. Recall that silica shells dissolve slowly in cold water while calcium carbonate shells dissolve rapidly in cold water. Therefore, silica shells are much more likely to reach the bottom in places with cold surface water, since they do not dissolve as much as calcium carbonate shells on the way to the bottom. Nonetheless, silica shells do dissolve on their way to the bottom, so if the water is very deep, the silica shells may dissolve away before reaching the bottom. If the silica shells reach the bottom without completely dissolving away, they can be buried and thus are no longer in contact with the ocean water that dissolves them. Siliceous ooze is more abundant than red clay beneath not too deep water far from land, because siliceous ooze is the remains of plankton who grow in the middle of the ocean, far from land, whereas red clay has to travel out from the land. Most of the red clay coming from the land does not reach the middle of the ocean. Like all sediments, red clay sinks in water, and red clay sinks as it travels from the land far out into the ocean. Most red clay ends up sinking closer to the land. A few lucky pieces keep getting lifted up by waves again and again while being pushed outwards by currents, or kept aloft by strong winds. Very little red clay reaches the middle of the ocean, so there is much more siliceous ooze than red clay sinking towards the bottom far from land. Beneath upwelling zones, a lot of shells are sinking, because there are a lot of plankton at the surface. All living bodies eventually become dead bodies. At the bottom of the ocean beneath upwelling zones, the water may become supersaturated with silica, allowing the shells to reach the bottom even if the water is fairly deep. In supersaturated water, all the water molecules are bonded with silica or other atoms and molecules, so they are unable to bond with and dissolve any more silica shells. Thus, siliceous ooze is found on the ocean floor in some fairly deep places below upwelling zones like the equator and next to west coasts, the east sides of oceans. Since some upwelling zones are in warm places, siliceous ooze is not only found on the ocean floor beneath the cold water of the polar oceans, but can be found in places you probably think of as quite warm. The deeper parts of the ocean floor like the abyssal plains and trenches are dominated by abyssal clay, also called red clay. Red clay consists of very, very small sediments which are carried away from land by currents and winds. Most clay settles close to land on the continental shelves and slopes. However, clay sinks very slowly, which allows a little clay to drift beyond the continental shelves and out into the middle of the ocean. Even though red clay piles up very slowly on the ocean floor, red clay is the dominant sediment on the deeper parts of the deep ocean floor because calcareous ooze and siliceous ooze dissolve away before reaching the bottom. Since the bottom is so far away from the surface, the shells spend a lot of time in contact with ocean water, which dissolves them. Red clay does not dissolve in water, and therefore it is the only sediment that can reach the deeper parts of the deep ocean floor without dissolving completely away first. As noted before, there is one major exception: in places where there are a lot of shells sinking to the bottom, beneath an upwelling zone, siliceous ooze can become the dominant sediment on fairly deep parts of the ocean floor since the water can become supersaturated with silica. Slide 8. Why study ocean sediments? Scientists spend a lot of time and money investigating ocean sediments, the muck on the bottom of the ocean, and I imagine that most people's first reaction is why bother? Ocean sediments provide clues about what was happening in the past at the location where the sediments are found. As we dig down deeper into the sediments, we are going back in time, learning how things were different in the past. And sometimes studying the past can be quite useful. Probably the most important reason to study ocean sediments is that they give us clues to where oil and natural gas deposits can be found in the ocean. In addition, the biological remains in the sediments tell us how phytoplankton and animal populations naturally fluctuate up and down with time, helping us better manage our fisheries, for example, avoid overfishing. Many deep-sea animals live on or in the sediments and they are extraordinarily diverse, that is, there are many different, unique species. Thus, deep-sea sediments can be a good place to look for new, unique chemical compounds that might be useful, for example, as medicines and green biofuels. Read the section on bioprospecting in Unit 13A for more examples. Sediments also contain pollution, and can be used to track down its sources. Climate change is an important area of research that uses ocean sediments, because changes in water temperature affect the kind of biological sediments that we find on the ocean floor. Thus, ocean sediments allow us to reconstruct how the Earth's climate has changed over millions of years, giving us insight into whether the present warming is normal or unusually fast. The answer is unusually fast. Slide 9. Copepods and the preservation of biological sediments. Unfortunately for oceanographers who study seafloor sediments, the small bodies of phytoplankton sink very, very slowly. In fact, it could easily take 10 years for them to reach the bottom of the ocean, plenty of time for the bodies to decompose and dissolve completely away. In addition, if by some miracle they reached the bottom of the ocean, they would be far away from where they lived at the surface. Even a small ocean current, say, of 1 centimeter per second, could push the falling bodies thousands of miles in 10 years. Thus, it should be very hard to use ocean sediments to learn about life in the ocean in the past, past climates, the locations of oil and natural gas deposits, and so on. The copepod, a small crustacean, and its digestive system come to our rescue, though. Copepods are one of the most abundant kinds of zooplankton in the ocean, so they eat a lot of phytoplankton. Some people call copepods the cows of the sea. Their digestive tract extracts much of the good stuff, like carbohydrates, from the phytoplankton bodies, but it does not digest the phytoplankton shells. It is like how we eat the meat of a chicken or cow, not its bones. Instead, the shells of the phytoplankton get crushed together in the copepod's fecal pellets. 99% of particles that reach the deep ocean floor are fecal pellets. Since the fecal pellets consist of dense calcium carbonate and silica shells smushed closely together, they are very dense and sink rapidly to the bottom of the ocean, in about 10 days. Because the fecal pellets spend little time falling, they do not dissolve very much on the way down and don't get pushed very far from where the phytoplankton and copepods lived. Thus, the sediments derived from these fecal pellets provide an accurate record of the kind of life that lived above the spot where we dig up the sediments. Thank you, copepods. I should note that other zooplankton contribute to helping material reach the ocean floor without dissolving. In addition to their fecal pellets, these zooplankton's shells and other kinds of waste materials add to the sediments on the deep ocean floor.